Okay, in our second video for this section, we are going to finish up a couple of the problems that we were looking at with sigma notation, and then we're actually going to start developing some intuition for how we're going to be approximating these actual areas here. So first up, let's take a look at example 6 here, which was a problem that you should have taken a look at and tried to do a little bit of between the last video and this one. So example 6 here is giving us a function. It's f of x equals the square root of x. And we're asked to compute the sum from I equals 1 to 10 of f of 5 plus I over 10 times 1 over 10. So we want to apply our kind of usual approach for doing this actual sum. So we're going to first identify where is I starting. In this case, I's starting value is 1. So I'm going to then take that starting value and use it in this expression for I. So in this case, I equals 1 is going to tell me that what I should be looking at is f of 5 plus 1 over 10 times 1 over 10. Great, so I've replaced my I by 1. To that, I want to add f of, now I need to replace I by 2, so 5 plus 2 over 10 times 1 over 10. And I want to continue this process, increasing I by 1 each time, up until I get to I equals, my upper limit here on I is 10. So we want to do this up until we get to f of 5 plus 10 over 10 times, again, 1 over 10. Great, so now that we've written this in a little bit easier format for us to actually do the computation, we can think about well, what are these numbers? Well, let's see. So we can start with 5 plus 1 over 10. We know that is 5.1. And if we think about what the function f does, f says take the square root of x, or take the square root of the input, rather. So here my x value is 5.1, and so what this f of 5 plus 1/10 works out to be the square root of 5.1. Then we still have this times 1/10 here floating around. So we've got times 1/10. Plus, next term in my sum, the next summand, is this f of 5 plus 2/10 times 1/10. 5 plus 2/10 is 5.2. And then I'm taking, f says do the square root, so I'm looking at the square root of 5.2 times 1/10. The next term in the sequence would have I replaced by 3. And so that would look, as with these previous ones, like square root of 5.3 times 1 over 10 plus square root of 5.4 times 1 over 10 times so on up until we get to this last term here. When we get to this last term, we've got 5 plus 10 over 10. 10 over 10 is 1, so this is f of 6. And that looks like the square root of 6 times 1/10. So if you go to the trouble of actually plugging all of these numbers into your calculator, you should find that this is approximately 2.36. Cool. So we have a number here. Next problem that I left undone at the end of the last video is example number 9 here. Use sigma notation to write down the sum 0.4 plus 0.1 plus 0 plus 0.1 plus so on. So we said our first step is kind of looking for the pattern here. And I'm going to, this is a tricky one, so it's okay if you didn't get it. But I'm going to maybe look here at maybe like 0, 0.1, 0.4, 0.9, 1.6, 2.5, and 3.6. And I'll maybe think about the fact that, well, except for the decimal place, these look a lot like the integer squares. So 1 would be 1 squared, 4 would be 2 squared, 9 would be 3 squared, 16 would be 4 squared, 25 would be 5 squared, and 36 would be 6 squared. But to account for the decimal place, I'll notice that each of these has been divided by 10. So 0.1 is 1 out of 10, or 1 squared out of 10. 0.4 is 2 out of 10, or is 4 out of 10. 0.9 is 3 out of 10. 1.6 is 16 out of 10. 2.5 is 25 out of 10, and 3.6 is 36 out of 10. So I'm adding up all of these numbers. And in fact, 0 here, well, sure, we can represent that as 0 squared out of 10. That's not wrong at the very least, and it fits with this pattern that we have for these other ones. And then we want to take a look maybe at this 0.1 and this 0.4 here, and we notice, maybe we remember that if you square a negative number, it becomes positive. So 0.1 here, we can represent that as minus 1 squared over 10. And 0.4 we can represent as minus 2 squared out of 10. So here we have this more general pattern that we're looking for that says what we're doing is we're summing up a bunch of numbers. So we have our sigma. And where we're starting, well, our starting value, our smallest I value is I equals minus 2 here. And there's nothing wrong with starting at negative numbers, so that is just fine. Our largest I value here is 6, so we can use that as the upper bound on our I values. And then what we're adding up here, we're adding up a bunch of I squareds divided by 10. Now maybe a good observation to make here is that, well, since I'm dividing all of these numbers in the sum by 10, if I want to factor out a 1/10, to maybe write this a little bit more simply, I could say that this expression here is equal to something like, let's see, 1 over 10 times minus 2 squared plus minus 1 squared plus so on up until I get to 6 squared. And so after factoring out that 1/10, we can do the exact same sort of thing with this sum here. So we can write this as 1 out of 10 times the sum from I equals minus 2 to 6 of I squared. So this is a nice property of kind of this sigma notation, that we can actually factor constant numbers out of it. I certainly can't factor out anything that involves an I, because the point is that when I changes, anything that involves an I also changes. So anyways, so we have kind of a couple of reasonable expressions that we could use for this sum here. Either one of those is completely fine. All right, great. So let's move on and take a look at how on earth this relates to our stated goals of actually computing some areas. So we're going to start by thinking about the area between the graph of a non-negative function and the x-axis. So we might sort of say, well, maybe our end goal is to compute the area of some shape that maybe has curved sides or something like that. But it's certainly going to be easiest if we start where only one of those side lengths is curved. We want the rest of our side lengths to be straight, and maybe later we'll deal with this problem where maybe we have multiple curved sides. So that's why we're sort of considering between the graph of the function and the x-axis, because the x-axis provides us with a nice straight line. So what exactly does this mean, area between the graph of a non-negative function and the x-axis? Well, what we're really kind of looking for here is if we've got this function that we have drawn. So maybe, yeah, let's look something like this. The area that we're looking for in the end is exactly this purple shaded region here. And we typically want to give ourselves a kind of starting and stopping place. So maybe we'll call the starting place A and the stopping x value B. So this purple area here is kind of exactly what we're looking to compute. And certainly we don't have any kind of formula for that, but we do have an assumption that we're allowed to start with, which is that we know how to compute the areas of rectangles. So maybe a reasonable assumption that we could make here would be to start by finding a rectangle that sort of looks like it might have roughly the same area as our function here. So we're going to talk about a couple different ways that maybe we could set up this rectangle that would provide us with a reasonable estimate of what this purple area looks like. So the first way that we're going to set this up is, well, we certainly want the rectangle, we want one of the rectangle's sides to be the bottom, to be the x-axis here, and we want it to go from A to B. So we know one of the side lengths of our rectangle, so the only question is, what should the height of our rectangle be? How tall should it be? And if maybe this is a graph of the function y equals f of x, as we commonly call functions, what we want to think about here is maybe we want to set the height of our rectangle to be some y value on this function here. So we have a couple of reasonable choices that we could pick for the height of our rectangle. One of which is the y value of the left endpoint here. So maybe we want to set that to be the height. And if I do that, and I draw out kind of this rectangle that I have here, great, then I can estimate my purple area with, let's make the estimates green here. Cool, so here is some rectangle that I've drawn, and the area, the idea here is that this green area should be pretty close to the purple area that we want to compute. We don't really know exactly what this, well, we don't exactly know what the purple area is, and we don't know exactly how the green area relates to the purple area. Maybe the green area is bigger, because certainly we've included some extra area kind of here in this green area that isn't included in the purple area. But also we have some purple area up here that isn't included in the corresponding green area. So depending on which one of those areas is bigger depends on whether or not green is an overestimate or an underestimate for purple. But at least, you know, we can actually have a formula for the green area, whereas right now we don't have a formula for the purple area. So let's actually take a moment to write down the formula for the green area here. So area is equal to base times height. So if I want to think about what my base length is here, if I'm going from A to B, the base length should be B minus A. And the height of this rectangle, well, I set the height to depend on this kind of left endpoint here. And the y value above x equals a is exactly f of a. Oops, I should move that up a little bit. Cool. So that is the corresponding y value there. And so base is b minus a times height is f of a. Cool. All right, so I have a nice formula for the area of that green rectangle. Let's think maybe about another way that we could set up a reasonable looking rectangle. Instead of choosing the left endpoint for the height of the rectangle, why don't we choose the right endpoint? For this particular function, it sure looks like these things end up being about the same. Maybe this right endpoint is actually a little bit higher up than that left endpoint there. But in any case, if we do this area here, let's see, we've got this right endpoint here, and the height now of my rectangle is exactly the y value above b. So the height here is f of b, and so the area for this estimate is going to be equal to, well, again, the base length is b minus a, and the height is f of b. Cool. All right, so these are maybe two reasonable ways of starting to approximate this area. But they don't provide us with very much information. We know that maybe they're kind of close to the purple area, but we don't know if they're bigger, we don't know if they're smaller. We really have very little information about how they actually compare. So let's go ahead and maybe we want to find a rectangle whose area is guaranteed to be larger than the purple area. And that's going to be a different type of estimate that we have. So here again, we're looking at the left endpoint being A, the right endpoint being B. This time what we want to do is we want to set the height of our rectangle according to the largest y value of the function between A and B. If f of x is a continuous function, we know that such a y value, in fact, must exist. That's one of our 251 facts. When you have a continuous function on a closed interval, so if we're including the endpoints a and b here, then there's some x value that maximizes the y values. So here we know, in fact, kind of where that y value is. It's right about in here. And if we want to set up our rectangle to have height according to that largest y value, and we want to then approximate the area, the purple area, with some green area, we get a picture that looks something like this. So this is kind of a nicer area formula, or a nicer area approximation, because we know this green area is bigger than the purple area. We've included all of the purple area, so kind of remember that purple here looks something like this. So all of the purple area here is included in the green area, and the green area has a little bit of extra out in addition to the purple area. So we know that our green is an overestimate here, but the issue is we don't know what the height of this we don't know what the height of the rectangle is, because we don't know what this x value is. But maybe we can give this x value a name. Maybe we could call it x upper star, where I'm using this superscript star here to indicate that this is the x value that maximizes the values of f between a and b. So here, if I want to think about what this y value is, or what the height of my rectangle is, I know the height of my rectangle is the y value here, and the y value above the point x star is going to be f of x star. Cool. So now we have a formula for my area, and it's a equals, again, the base is going to be b minus a, and the height is going to be f of x star. Cool. So let's see. So maybe we want one more type of estimate, and this is going to be a lower bound for the purple area. So this time, instead of looking at the largest y value for my height, I'm going to want to look at the smallest y value between a and b for my height. So that occurs right around here. And so let's go ahead and draw out a rough picture of that rectangle. And my estimated area is green again. So area under this rectangle. And then the area that I'm trying to compute is this purple. So certainly green here is an underestimate for purple, because purple includes all of the green area and then some more. And if I want to talk about what the height of my green rectangle is, maybe I want to again give myself an x value here. So this time I'm going to call it x lower star to indicate that this is the x value which minimizes the values of f. My y value is, or my height of my rectangle is then f of x lower star, and the area of this rectangle is b minus a, the base, times the height, f of x lower star. Great. All right, so this provides us kind of with these four nice approximations of the area here. We have a left endpoint approximation using making the height just the left endpoint. The advantage of this is that we have a very nice formula for it in terms of just b and a and f. Right endpoint is symmetric. It has the exact same advantage. The disadvantage of these first two approaches, however, is that, well, we don't really know how this green area relates to the purple area. Is it bigger? Is it smaller? We don't know. On the other hand, we could look at these upper and lower approximations. So these are nice because we know the answer to the second question. We know that, for instance, this approximation is larger, the green area here is larger than the purple area, and the green area here is smaller than the purple area. But the problem is we don't really know what this x upper star and x lower star are. We have some techniques in calculus from 251 that allow us to find these things if we know what the function is, but that's kind of an annoying process. You have to take a derivative and set it equal to 0 and do some solving, and then you have to check some endpoints. So really, that's not the ideal process that we want to be going through to compute these estimates. But for the moment, this is kind of the intuition that we're going to be working with. And in the next video, we'll talk about actually improving these estimates and sort of seeing how we can do better.